All right, so this will be the sixth video in our Unit 3 so far. We're going to take a step back, not go into the conservation of energy just yet, but we'll maybe do that in the future in the next video. So this is Work Energy Power Unit number 3. This is part 3. We're still talking about energy, kind of an introduction to energy, and learning target is I can calculate energy. So I'm sure you can guess that this means we're going to do a couple of practice problems. So we'll do problems and try to, these should be pretty quick. They shouldn't take too long and they should be pretty straightforward. So we'll do problem number 1. You have a mass that is traveling at some speed. So the mass is 100 kilograms and the velocity of this object is 10 meters per second. And I want to know what is the total kinetic, or what is the kinetic energy of this object. So I'll let you pause the video, take a few seconds, try to figure it out. Shouldn't take you very long, so go ahead. Okay, so welcome back. Let's give this a shot. Our kinetic energy equation is T is equal to 1/2 mv squared. Our mass is 100 kilograms. Our velocity is 10 meters per second, and we square that. And when we do that, we'll get 100 times 100, which is 1, 2, 3, 4, 10,000, and we still have that 1/2. Our units are kilograms times meters squared over seconds squared, which indeed is a joule. So if I divide 10,000 by 2, I will get 5,000 joules. So this object, because it is 100 kilograms and has a speed of 10 meters per second, has an energy, kinetic energy of 5,000 joules. Problem number 2. Let's say we have that same mass, so mass is still 100 kilograms, and this mass is a distance, or is above the ground at a height, say h is equal to 5 meters. I want to know what the energy it has because it is that high off the ground. What is its gravitational potential energy? U sub g is equal to mass times g constant times y. Our mass is 100 kilograms. G is 10 meters per second squared. And our height, again, or y, whatever, is 5. So if I take that 5 times 10, that's 15, or 50, times 100, which would be 5,000 joules. We can double check our units. That's a kilogram times a meter per second squared times another meter, which is a kilogram meter squared over second squared. And yes, that is a joule. So 5 meters up above the ground, mass of 100 kilograms gives us 5,000 joules. Try one more. We'll do a spring one this time. So we want to know how much energy is stored in a spring where the delta x, the compression distance, is negative 0.10 or 10 centimeters, 0.10 meters or 10 centimeters. We'll say the K constant is 150 newtons per meter. And we want to know the spring potential energy, U sub S. So I'll give you a moment or two to try to work that out, and we'll be back. Okay, welcome back. So U spring, we know the equation, that's 1/2 kx squared. Our K value is at 150 newtons per meter, and then x squared, that's 0.1 meters squared. If I plug that into my calculator, I get 0.75, and my units are going to be, well, I have from K value, I have newtons times meters, and then I have mass or distance squared, so I get meters squared. One of those meters on the top will cancel out the newton per meter on the bottom, and I will end up with newtons times meters, which we said was a joule. So indeed, we get 0.75 joules. Now let's just, I have been checking these units here on this unit here, our units of newtons per meter times meter squared, make sure that they end up a joule. And the reason why I'm doing that is because if I made a mistake in my algebra, I could easily have something like newtons per meter cubed, as if I divided by x squared instead of multiplied. And if that were the case, I would know right away that's not an energy unit. A newton per meter cubed doesn't even exist. I don't know what that is. And so I would think to myself, maybe I screwed up. I need to go back and double check my work. So when you do these problems, you should really, really be checking your units just to make sure that they match, that they give you joules or they give you newtons or they give you whatever. Because if they don't, then you've made a mistake algebraically and you probably need to go back and fix that. So anyways, this is how we calculate our energy. It's pretty straightforward for just calculating the energy. This is the kind of thing that you'll see on your first progress check, but it's, again, not terribly bad, right? It's pretty straightforward. It's once we start getting into conservation of energy in the next unit or the next video that things get kind of weird and we have to do a lot of heavy lifting, with the mental load and stuff. So we'll see you back on that next video. Until then, have a good one.